In this lesson, we are going to be using some very popular linear models. They're easy to set up and explore and are an important tool for beginning your data analysis. Before we begin, let's load the Cars 93 dataset. Let's make sure to load the mass package. And then we're going to load the Cars 93 dataset using the data function. Then we're going to attach it so we can reference the variables. Now, to create a linear model, we use the LM function. The argument that we enter is the function that we are interested in exploring. First, you list the dependent variable. And for now, why don't we set the dependent variable to be weight? And we're going to set that equal to some independent variables using the tilde. We can't use the equal sign because the equal sign is an assign operator, so R would get confused if we ran into that. So generally, when we set up equations inside of a function, we use the tilde. So now let's pick some independent variables. It needs to be MPG, all capitalized. In this case, weight is the dependent variable, and we are regressing it on some variables of Cars 93. Now, the simple output only gives us coefficients. We can easily extract more info, however, using the summary function. So I'm going to assign a variable, this model. And now we can use the summary function on this model, and we'll get a lot more information. So there's a lot to go over here, and soon we'll talk about how to extract specific pieces of information from a linear model. For now, let's focus on this summary output. First, it gives you the call or function that was entered into the LM function, then a summary of the residuals of the model. Each observation makes a prediction of what the weight should be, and the residual is the error between the predictions and the true weight of the vehicle. In this case, the model was off by as much as 530 pounds for one vehicle. Next, we get to look at the model coefficients, including the estimate, standard deviation of the estimate, the t-value, and the p-value associated with that t-value. Next to that, you will see 3 stars for each coefficient. These correspond to significant levels just below the coefficients. You can see it here, significant codes. 3 stars means that it is very significant and a strong predictor of the weight. Lastly, we get some more information on how the model performed overall, including the R-squared measure, adjusted R-squared, F statistic, and p-value that all the coefficients are different from 0. Now, an R-squared or adjusted R-squared of 1 means that the independent variables perfectly explain the dependent variable. Our model comes up with 0.9, which is very good. Now let's discuss the intercept and how we can modify it using the iris dataset. So let's load it into our environment. I'm going to attach the iris dataset. Now I'm going to create a new variable called fit, which is going to be a linear model. We're going to regress petal length as a dependent variable on petal width. Plotting a linear model is very helpful. It produces 4 plots describing the model output. So why don't we set up our future plot to have 4 different panes? I'm going to expand my plot window to make sure that everything can plot okay. And now I'm going to plot the LM object, which is called fit. And we can see these 4 different plots that show up. Now when we plot the linear model, we get 4 different plots. We get a residual plot with the outliers labeled. You can see that there are 3 in this case. Observation 115, 135, and 108. There's also a normal QQ plot for the residuals, so we want the residuals to follow a normal distribution. And then lastly, there's a scale location plot, which describes how the distribution of errors change, and a leverage plot. Now you can decide whether you want to take out the intercept using +0 in the function. So if we look at a summary of the model fit, we can see that there's an intercept of 1. Sometimes you may want the model to converge to 0 at the intercept. So if you were interested in doing that, just add a +0 as one of the independent variables. And if we plot this, we might see some changes. And yes, you can see there were some changes. So making the intercept 0 is not the best for this situation. We can see that the normal QQ plot has now deviated away from the QQ line. Now let's just plot 2 of the variables as a scatter plot and add some ab lines. First, I'm going to clear all my plots. so then the single plot will take up the whole window. Now we're going to add two different lines, one with an intercept and one without. When you use the abline function with a linear model object, it's going to produce the linear regression line. Here's the one with an intercept of 0, and if we take out that 0 intercept, we'll see it shift. Now, allowing the LM function to find an intercept will generally create a more robust and accurate model, but there are cases where you may not want to use an intercept. Now, there's also the GLM function, which stands for Generalized Linear Models. This allows us to look at other types of regressions, such as a logistic regression. And it is just as simple as the LM function, except that it requires an additional argument which tells it which variance function to use. In this lesson, we discussed how to create linear models and begin exploring the relationship between variables. It is a very powerful tool that is used frequently in the statistical world and will be useful in any analysis.